This conference will now be recorded.
Very good evening, students. Today I have come up with various questions discussions on electrostatics. So here what we are doing, we are taking up various type of questions from various subsections of electrostatics like electric charges, then electric field, electric potential, etc. So part by part I'll discuss today. Today it is electric charges and field. Okay, so these questions are actually being asked in various competitive exams as well as board exams. So these questions are going to be some questions will be little bit easy just to build your concept. Some questions will be medium and some questions may be tough. So we'll discuss all type of questions over there. Okay, so let us start with this particular question. Which of the following charges cannot be present on an oil drop in Millikan's experiment? So you might be knowing that Millikan oil drop experiment is the experiment where the charge of electron, okay, electronic charge has been quantified. All right. So charge of electron was quantified or determined by Millikan's oil drop experiment. Scientist Millikan has done that. Okay. And the experiment is called Millikan's oil drop experiment. So here there are three different charges given, like 4.0 into 10 to the power minus 19 coulomb, 6.0 into 10 to the power minus 19 coulomb, and 10.0 into 10 to the power minus 19 coulomb. See, these are three charges, different charges. So here the question is whether, like, which of the following charges cannot be present on oil drop in Millikan's oil drop experiment? And the fourth option is all of them. That means none of these charges can be present in the oil drop. So here, see, the concept you have to recall is the quantization of charge. Quantization of charge. So what does that say? That says quantization of charge, this principle says that any charge can be expressed in terms of integral multiple, in terms of integral multiple of the fundamental charge or a basic unit charge, and that is here E, the charge of electron or electronic charge. Okay, electronic charge, if I take the magnitude, that electronic charge is becoming 1.6 into 10 to the power minus 19 coulomb. So any charge can be expressed as integral multiple of this. That means, see, this is integer number. Okay, this can be 1, 2, 3. It cannot be any odd number, or like it cannot be half integrals, etc. Okay, so all these things will come like 4, 5, 6. So this all integer numbers. This is an integer number. Okay, it is an integer number. So what you learn from here, are any one of these three charges is expressing this fact whether 4.0 into 10 to the power minus 9 coulomb is 4e? No, because 4 into 1.6 it has to be. Okay, that means this has to be 6.4. It can be, see, this is also not integral multiple of e. Even this is also not integral multiple of e, neither this one. So all of them cannot be present, not only in the Mendicant drop experiment. In the universe, charge exists in terms of integral multiple of e. Okay, so all of them cannot be present. Okay, this is the answer. So option A, like option 4 will be the answer for this question. All right, now look this question. So this is actually, I would have given this question first, then I would have asked that question. I'm sorry for that. So the sequence has been like it is. See, if I would have asked this question first, then you would have answered easily the question I have shown in the first slide. So in nature, electric charge of any system is always equal to half integral multiple of the least amount of charge, 0 square of the least amount of charge, integral multiple of the least amount of charge. So this is actually saying the fact of quantization. Okay, so quantization of charge that I had discussed in the previous slide. Okay, I would have given this question in the beginning so that you learn this, then you can answer the previous question. Okay, anyway, I apologize for that, but anyway, you can understand that this, see, this is just this one, integral multiple of least amount of charge or unit charge. Okay, so in nature, electric charge of any system is always equal to integral multiple of the least amount of charge, that is actually electronic charge. So it can be 1e, it can be 2e, it can be 3e, 4e, 5e, like that, but it cannot be half e, or neither it can be 5 by 2 e, it cannot be that. Okay, so it will be integer number. Okay, integral multiple of least amount of charge, that is electronic charge. All right, so the fourth option will be the correct answer for this question. Now this question says, consider a neutral conducting sphere. Consider a neutral conducting sphere. A positive point charge is placed outside the sphere. Okay, the situation is something like this. This is so far neutral. This is a conducting sphere. The net charge on the sphere. See, if a positive charge is placed at this particular position, just near this, what will happen? This is conductor. Okay, so this is conducting sphere, so there will be induction. Okay, and due to that induction, this sphere will be getting charged. So what will happen? So let me show you the options here. Negative and distributed uniformly over its surface. Negative and appears only at the point sphere to the like, see, negative. See, the question is that the consider neutral conducting sphere. A positive point charge is placed outside the sphere. The net charge on the sphere. Okay, net charge. Okay, what is that net charge? It is asked. So the options are negative and distributed uniformly over the surface, over its surface. Negative and appears only at the point on the sphere closest to the point charge. That means it is saying whether it will be just negative charge here, okay, or there will be negative charge all over the sphere, and negative and distributed non-uniformly over the surface, and 0. So look here, I just before I answer, let me tell you the concept over here. Any neutral body will have equal number of negative and positive charges. First of all, equal number of negative and positive charges. So when you bring a positive charge over here, you know what will happen? The positive charge at this particular position or near to this positive charge will be repelled by this positive charge, so they may go this side. Okay, so there will be excess of positive charges over here. At the same time, since the positive charges are going there, there will be negative charges appearing here. So the number of positive charges going at the rear surface, those many numbers of the negative charges will appear near to the positive charge outside. Okay, so you will see this thing. Okay, but net charge, what is that? Net charge, since it was neutral earlier, net charge is going to be zero, because see, this positive charge, negative charge, ultimately they will be cancelling each other, and you are not going to take the charges. See, by doing this, see, just keeping a positive charge, positive point charge near the surface, you are not taking away any charge from the sphere. The charges are there, but they have got some displacement from one another. Okay, so because of that, you can see some appearance of charges on the surfaces in the near the point, the surface near the point charge, there will be positive charges appearing, and to the rear surface, the negative charges will be appearing at the surface near to the or closest to the positive point charge, and positive charges will be just going to the other surface. Okay, but what is the net charge? Net charge is going to be zero only. Okay, because earlier it was neutral, so there was no excess charge. Equal number of positive and negative charges will be there, so net charge is zero. Okay, net charge will be zero. All right. So let us go to the next problem. Okay. Sorry. Excuse me. Okay, so this question says force between two identical spheres charged with the same charge is it? Okay, let me just draw the situation. So there were two identical spheres like this. Okay, this may not be looking like identical, but you just take this, that these are identical spheres and they had actually same charge, suppose q initially, and let us say they are separated by some r distance from each other. Okay, then the force between them was F, and that can be written as K Q square by R square. This is a simple thing. Now look, if 50% charge, 50% of charge of one sphere is transferred to the other sphere, then what will be the new force? See, suppose 50% of charge, like say Q by 2, has been transferred to the other one. So this guy has got now q by 2, but this guy will have q plus q by 2. So this is where people do the mistake. Okay, you might be taking q by 2 both cases. No, it has got some charges, so q by 2 extra. So what will be the force then? A prime, that will be k. K is actually 1 by 4 pi epsilon naught. In SI unit we are taking excuse me. So in this case, I'll write down the charge q1 q2 by Distance between them, that is this. Now look what we are getting. See, this 3 by 4 will come 3, and in the denominator there are 2 into 2, so 4. So I get k q square by r square, and this is nothing but f, isn't it? So what I get? This is nothing but f. So I get 3 by 4 into f. So the new force will be 3 by 4 into f. So this is the answer. This is very simple, but these are the questions which will help you to develop your conceptual understanding. These are very simple questions, in fact. Okay, so this question says 2-point charges placed at a distance r in air exert a force F. Okay, let us just take 2-point charges. Some charges. Okay, let me take positive charges itself. So 2 positive charges, Q1 and another one is Q2. Okay, they are separated by a distance r, say, and if these 2 charges are kept in air, okay, in air, then what will be the force between them? That is given as F, and that I can write actually K by, okay, let me not confuse with this. Okay, so it will be, Q1 Q2 by 4 pi epsilon naught r square, right? So here this epsilon naught, it is just for air, so permittivity in the free space. Okay, but when these 2 charges are placed inside a medium, see the distance at which they exert the same force, the distance at which they exert the same force when they are placed at the certain medium of dielectric constant K, then what will be the distance when the same force F will be exerted by both? Let me write down the force, like equation of the force between the charges when they are placed in a dielectric medium. So that can be written as A prime is equal to Q1 Q2 by 4 pi, and in place of epsilon I have to write K epsilon naught. This K is the dielectric constant of the medium, okay, and this is r square. Okay, let us take this as r1 square because this distance is not going to be same now. Okay, we have to find out the distance where these forces are same actually. Okay, the magnitude of these forces are same, so that distance r1 we have to find out. So this, according to the question, f prime is f, and from there we can write q1 q2 by 4 pi epsilon naught k into r1 square, and that will be equal to q1 q2 by 4 pi epsilon naught r square. Now look, I have common these things, I can strike them out. What we get is k r1 square is equal to r square. Okay, from here what I can write? I can write see r1 is equal to r by square root of k. Okay, so this is actually the distance where the force will be same between the charges, like force between the charges will be same when they are kept in the medium. Okay, I mean to say the force, earlier the force was F when they are kept in the air, and now this is the distance where distance between the, so r1 is the distance between the charges inside the medium when the same force F by magnitude, obviously the same magnitude of charge will be acting between them, okay, or exerting between them. So see, 3, option number 3 will be the answer for this question. Okay, This is very simple question, and also the question from the example, maybe example of NCERT textbook. So in the figure, force on charge A in the direction normal to BC. Obviously, direction normal to BC will be how much? We have to find out. Okay. So you know the charge. See, charge A is this. See, all the charges are Q, like having the same charge, Q, 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 and this A. As you see, this is actually equilateral triangle. Now I have to find out charge on A. So I have to find out charge on A due to B and due to C. So both are positive charges. So you know this positive charge will be pushing this in this direction, because there will be repulsive force acting on them. Okay, like this. And the charge C also will push this in this direction. Okay, let me draw this figure then. I'm sorry. Let us say this is an equilateral triangle. So there is a charge over here, here, and here. All the charges are actually same. So look, this is B charge and this is C. This is A. So this B will actually push this direction. Okay. Let us say this is force on A due to B, and this, I'm sorry, this direction, C will push in this direction. Okay, so this is the force on A due to C. All right. And now this angle, see, this angle is actually 60 degree. Now if I just draw an axis system like this way and this way, if I just consider a y-axis here, x-axis here, so you look, these two forces are making certain angle. See here, since this is 60 degree and these two forces are actually equal. Okay, these two forces are equal in magnitude because all the charges are q and the distances are also same, a. All right, so what we get, this angle is 30 degree, this angle also 30 degree. So these two forces will have components. Okay, one along this way, this FAB. See here, I can say FAB sine theta, sine 30. Okay, and along, see, along the vertical direction there will be FAB cos of 30 degree. Okay, similarly, due to this C charge, there will be component along this way and along vertical direction. So look, this FAC, this is sine 30 degree. See, FAC by magnitude, FAC and FAB. So by magnitude, these are same, and they are like they are. So these two components will be actually balancing each other. So ultimately, what we'll get the force. So the net force on A will get as, see, two components I'm getting here the side. So 2 into FAB or FAC, whatever you take, FAB cos of 30 degree. Okay, so this is the net force. Now we have to find out what is FAB or FAC. So that is very simple, as you know. So here 1 by 4 pi epsilon naught is taken as K. So I can write, so FAB is equal to K Q square by the distance is A over here, isn't it? Okay, distance is A. So A square. Okay, this is the force, and obviously this will be repulsive force. Okay, repulsive force. And see, now there will be, okay, so the net force here I can write 2 into k q square by a square into here cos of 30° is √3 by 2. Okay, cos of 30° is √3 by 2. So this two will cancel each other. By a square. So what we get is this one. So the fourth option will be the correct answer for this question. Okay, I hope this is clear to you. All right, so let us move on to the next problem. Okay, so this problem is again very interesting problem. See, there are two charges 9e and 3e are placed at a separation r. Let me write it here. So this is one charge. Oh, sorry. This is another charge. So let me take this as 9e and this is 3e. They are separated by distance r. The distance of the point where the electric field intensity will be 0. Okay, so in between them, okay, there should be a point where the electric field intensity will be 0. See, how do we define electric field intensity? You know, suppose I want to define electric field intensity for some charge q, say, at a distance r. Then you have to actually keep one unit charge, suppose 1 coulomb charge you are keeping here, positive charge, and the force exerted by this q charge on this 1 coulomb charge at a distance r is actually giving you the intensity, field intensity, electric field intensity at that point. So now let me just consider that let us say at a point P, which is x distance away from the 9e charge, there will be 0 field intensity. That means what? The force on 1 coulomb charge exerted by this 9 coulomb and the force exerted by 3 coulomb will be balancing each other, isn't it? That means, you know, look what I can write. So q e into 1 coulomb, let me write 1 by 4 pi epsilon naught. This distance is x square. Okay, this is the force on 1 coulomb. This will be exactly equal to the force 3e into 1 divided by 4 pi epsilon naught, and see this distance is actually r minus x. Okay, so let me write this as r minus x square. Okay, so these two forces will actually balance each other, so I can actually cancel out this 4 pi epsilon naught, 4 pi epsilon naught. Okay, let me write is, see, x minus r minus x whole square divided by x square, and here it will be, see, e I can cancel, so this is 9, not q, this is 9e, 9e, so it will be 3 by 9, that means 1 over 3. Further, I can just take the square root, so r minus x divided by x, that is 1 by square root of this. All right, so now I have to find out what is this x. So if I do this simplification a little bit, let me just do it here. Let me take this place, so I'll get √3 r √3 x is equal to x. Okay, that means, you know, this square root of 3 plus 1 into x is equal to square root of 3r. So we have to find out what is x. X is equal to square root of 3r divided by square root of 3 plus 1. Okay, so this will be actually the distance from 9 coulomb charge. Now look this are the options. So that distance, the distance of the point where the electric field intensity will be 0 is r by 1 plus square root of 3 from 9 charge. That is not true, as we have seen. So square root of 3 r divided by square root of 3 plus 1 from 9 charge. See, this is true, and others I'm not reading, you can just see sometime. So this is not true from, see, this value is same, but this is not x. Okay, x from 3 charge actually r minus x you have to do. Then what you find will be from 3 charge. We can actually find out. If you want, we can do that also. So in that case, you know what, okay, let me just calculate what is the distance from r minus x. What is r minus x? Okay, so r minus square root of 3 r divided by square root of 3 plus 1, this one. Let me take this r common, then what we get, root 3 plus 1 minus root over 3 divided by root 3 plus 1. So root 3 cancel each other, so r by 1 plus root 3. So r by 1 plus root 3, that should be the distance from root 3 plus 1. So that should be the distance from 3 charge. Okay, so all other options are obviously wrong. Okay, so this is second option is the correct answer for this question. Okay, now this question is very interesting question. So a ring of radius r, capital R, I'm sorry, so a ring of radius capital R is charged uniformly with charge capital Q. The electric field at a point on its axis at a distance r from any point on the ring will be what out of these 4 options? Okay, so just by seeing the options we may not be able to guess. Let me first of all draw this ring, and this is obviously positively charged as you see, and it is uniformly charged. Okay, now if this is the center, this is the axis of the ring, and the question says that at any point on the axis at a distance r, so this is any point on the axis, any point on the axis at a distance r from its any point on the ring. Suppose this is one point, so from this point this distance is r, this is what is given. Okay, and the radius, as you know, this is capital R. Let me say that point is x distance away from the center. Let me say this is the center, and let us take this point P. Okay, so here you have to find out the electric field at a point, this point, okay, this particular point, from any point charge. Okay, so how do you find out that? You know, there is a process, lengthy process to do that. I'll just discuss a little bit. So how to do that? You know, here we know that electric field intensity is given by Q by 4 pi epsilon naught r square. So here, see, this is a linear charge, like this is a ring, so it has linear charge density. The total charge is Q. I have to actually consider segment by segment. I can just take a small segment, okay, just opposite point you can take another segment. Suppose one segment is here, one segment of the ring is here, another segment of the ring I consider here. Now see, this has certain charge. What is that charge? I can find out. Let us say this has got length dl. This element has got, or segment of the ring has got length dl. So what will be the charge in this? I have to first find out. So let me take that charge as dq. But what is that charge? Linear charge density. That means the whole charge given divided by the whole length of the ring, that is 2 pi capital R. This is the linear charge density into the length of that particular segment. So this is the charge. So I can write the electric field due to that particular element or segment at this particular position P, in fact towards it, okay, towards it will be say Q by 4 pi epsilon naught R square into dl. Okay, so this is one part of it. But anyway, see, look, this is actually going to be in this direction. Okay, somehow it will be acting this way, electric field. Let us say this is dE. Okay, all right, this is actually, so Q by 2 pi R, I'm sorry, this is there, and obviously here there will be Q by 2 pi capital R as well. Okay, so we have to let me not worry about this. Let me just take this as dq itself. Okay, this part, the whole part is dq by 4 pi epsilon naught R square. Now this charge, suppose this angle is theta, which is making with the axis. Now it can have two components. One is this way, d cos of theta. Another component will be in the downward direction, d sin theta. Okay, now if I take diametrically opposite segment here at this particular position, so look, this also will be, I'm sorry, this will act in this direction, and this eventually also will have the same magnitude of the electric field. And see, this angle also will be theta at equal angle. Okay, so it also will have two components, one along this way, d cos theta, okay, and this component will be actually cancelled out, d sin theta. Now see, you have to find out the electric field along the axis due to a point. See, electric field due like from any point on the ring, from any point on the ring, from any point on the ring, only single point on the ring. Anyway, the d sin theta will be cancelled out. So you know, you will get electric field dE cos of theta. This is the electric field along the axis due to a segment, due to a point on the ring. Okay, so this can be written as, now cos theta, how do I write? See this, if this is theta, this also will be theta. So how do I write cos of theta? So cos of theta, you can write, this is x, this is r, so x by r, you can write that. So let me just write this dq by 4 pi epsilon naught r square into x by r. Now if you want to find out electric field due to the whole ring, then you have to integrate. So integration, so electric field E will be this integration of this thing, and see the whole thing will be here x by 4 pi epsilon naught r cube and integration will be on the charge dq. So dq integration will be total charge q only. Okay, so I can write the electric field due to a ring as at any point of the axis will be qx by 4 pi epsilon naught r cube. Okay, let me just go to the next point, sorry, next slide. So what I get is this qx divided by 4 pi epsilon naught r cube. So what is r over here? R may not be known to us, but what are the parameters known? This distance from the center I know, and radius of the ring I know. So if I want to express this small r, see, I know small r square is equal to x square plus r square. If you are having problem, let me draw it here. So this is r, small r, this is capital R radius, and this is x. This is the point. Okay, so from here I can write this, isn't it? Now see the options over here. Options are in terms of smaller and capital R. That means I have to get rid of x. Okay, so get rid of x. So what I get, x square is equal to r square minus capital R square. Okay, so from here x is equal to square root of r square minus capital R square. Now look, if I put this value over here, okay, let us just write small r first of all. Here electric field is qx divided by x, doesn't matter, let me just do it. Yes, so 4 pi epsilon naught, this is actually, say, r cube means it is x square plus r square whole to the power 3 by 2. Okay, just look at this. Now I'll just put the value of x over here. Put x into this. Okay, let me put that, and then what I get, E is equal to q x is square root of r square minus capital R square divided by 4 pi epsilon naught this, and say x square is this one. Let me put it here. So this is r square minus r square, this is plus r square, and whole to the power 3 by 2. Okay, look, then this cancel each other, so this will be actually, see, q, this is square root of small r square by minus capital R square divided by 4 pi epsilon naught, and this will be r cube. Okay, so finally I'll clean everything and write down what I have got. E is equal to q small r square minus capital R square whole to the power half divided by 4 pi epsilon naught r cube. So this is the answer I have got. So this I can write as k cube by r cube into, this is r square minus capital R square whole to the power half. Okay, so option 3 will be the correct answer for this question. See, dear students, just for your understanding, I have just done this elaborately, but don't get so much uh, depressed to see or less enthusiastic, okay, by saying that rigorous calculation. But you can just remember this formula, that electric field due to a ring on its axis will be given by qx divided by 4 pi epsilon naught x square plus capital R square whole to the power 3 by 2. So you can just keep this in your mind, and there is a similar formula in case of magnetism also, the magnetic field due to a ring on its axis. Okay, so same kind of formula is there in that also. Okay, so this is not very tough to remember. If you remember this, from there you can just do this calculation. Okay, I had actually shown you how we get this electric field due to a ring at any point of the axis. So you don't no need to do that rigorous calculation. You just remember this, and then from there you can just replace, like you just get rid of x. So you have to write down your answer in terms of smaller and capital R. That is what was the thing. Okay, all right. See, if I know this, then rest of the thing is this much. Okay, this is very simple. All right, we'll go to the next problem. This is not very tough question. Let us see. The electric field in a certain region is given by this. So electric field, let us write the magnitude itself. So K by x is cube. So K, you have to find out the dimension of K over here. Okay. Look, this is electric field, and this is X. Let me tell you here. See, this has got actually dimension of force into charge, Q into, I'm sorry, A by Q. Okay, electric field has got unit force per unit charge. Now this is K by x is Q. So you have to find out the dimension of K. So let me just keep this K alone, and see, I have to write the dimension of this and dimension of x is cube. Okay, x is length over here obviously, and this is a ml t to the power minus 2, and see this q, I can write q is ampere into time. So this is here, and see this has got dimension l cube. So finally what we are getting, see m is as it is, l will be to the power 4, so t to the power minus 3, okay, and a to the power minus 1. So this is the dimension. Look, this option 3, m l to the power 4, t to the power minus 3, a to the power minus 1. So option 3 will be the correct answer for this question. Okay, now another good question over here. So electric field at the center of a semicircle of radius a having linear charge density lambda is given by. I'll tell you two things here, like just by remembering formula and how to derive also. I'll tell you here how to calculate rigorously and how to keep it, like do it very like if you just remember a formula, that will help you to find out the electric field due to a semicircular or any kind of arc. Okay, for any kind of arc, electric field by that arc, electric field produced at the center, I think center, yes. So find the electric field at the center of a semicircle of radius a having linear charge density lambda. So charge density is given. So for any kind of arc in general, for any kind of arc, let me write it here. For any arc having charge density lambda, electric field at the center, okay, electric field at the center will be given by at the center of that arc will be given by what? This simple formula, 2k, k is 1 by 4 pi epsilon naught, okay, 2k lambda by the radius of the arc into sine the angle subtended by the arc at the center. Angle subtended by the arc at the center, if suppose that is theta divided by 2. Let me just give you a simple example. Suppose there is an arc like this, some arc. Okay, so this radius is r and this angle is theta. Okay, suppose the lambda is the charge density. Then this, say, electric field at this particular position, this is the center. Okay, center of the arc. So at this point the electric field will be given by 2 into k is 1 by 4 pi epsilon naught, okay, into the r is the radius, and here sine theta by 2. This is the formula. Okay, this is the formula, and if you can just strike this out, later you can do many kind of application, like application of this. Now here you have got a semicircle. Okay, so this arc is making an angle 180 degree, right? So theta is 180 degree here. Radius is given as capital R and lambda is given. What else you need? So what will be the electric field at the center? That means at O, electric field at O will be 2 into k sine, lambda will be there, sine 180 degree by 2 divided by r. Now let me write k is 1 by 4 pi epsilon. So 2 lambda here sine 90 degree divided by 4 pi epsilon naught r. Now do a little bit more calculation, like simplification. So sine 90 degree is 1, isn't it? So what do you get? So you get lambda by 2 pi epsilon naught and r. So this will be the answer, lambda by 2 pi epsilon naught r. Look, lambda by 2 pi epsilon naught r. Here the radius was given a, not r, a, so it will be small a. Here it was given a radius, so a, lambda by 2 pi epsilon naught a. So option 3 will be the correct answer for this question. Now some of you may be asking me, sir, how to derive this formula itself. Okay, for a semicircular arc, let me find out if you have to calculate in your board exam, how to calculate that. Okay, so this has got, suppose, positive charge all over uniformly distributed, and charge density is lambda, and this is the center. Here you have to find out what is the electric field. See, I can consider a very small element of this length element. Okay, and due to this element, see, there will be electric field at this point. The direction of the electric field will be something like this. Look this. Okay, like this. And let us say this has got length dl, and suppose this element is at an angle, this is theta, and this angle is d theta. Okay, so this dl can be written as, see, if this is r, capital R, this can be written as, dl can be written as r d theta. So I have got the length. So what will be the charge due to this element? So that is dq, that can be written as lambda into dl. That means r into lambda d theta. Okay, now let me just draw one perpendicular here. So this angle theta. Now look, this electric field, if this angle is theta, see, the d theta will be very small, obviously. So I can just take this angle as theta itself. d theta will be very, very small. So this angle, let us take that theta itself. So this is theta, right? If this angle is theta, then see this electric field, let us say, due to this element will be dE, which is making an angle theta with this radius. So it will have two components, one along this way and another one along this way. So here is in this direction it will be dE cos of theta. Along this direction it will be dE sin theta. Now if I consider another element exactly here, like diametrically opposite point somewhere here, okay, at an angle theta like this, it will have, see this angle theta, so there will be dE electric field. Okay, same dl length, I am just considering dl by r d theta and all those things. So this dE will have one component here due to this element, so that is dE cos of theta, and another component along this way there will be dE sin theta. That means, you know, if I consider a point or an element over here, there will be a corresponding element exactly at the same angle on the other side or diametrically opposite position, which will cancel, see this d cos theta with this d cos theta, isn't it? They will cancel each other. So finally, you know, you will get how much electric field? Electric field in this direction, okay, perpendicular to this radius, okay, and that will be 2 dE sin of theta. And this I have done considering both the sides. Now see, my limit will be like this. So if I now do the integration, I'll do the integration for this particular part, okay. So this angle is 90 degree, isn't it? So theta starts from here somewhere, okay. Theta goes from 0 to 90 degree. If I just want to calculate the total electric field at the point O, that will be 2 dE sin theta, right? An integration of this, and where theta limit will be 0 to 90 degree or pi by 2, whatever you say, pi by 2. Let us write as pi by 2, okay. Now let us put the value of dE. What is dE? dE is actually dq by k dq by r square. What is this r? R is capital R itself. This is capital R itself because it is semicircular art. So this is this. What is dq? dq is actually r lambda d theta, okay, divided by, here k will be there, divided by r square, and this r will cancel each other. So what I get, dE as k lambda d theta by r, okay. This is the point here. Now let us see, 2 will be there, d I'll write, see k lambda by r, these are constant, I'll just take them out of integration, and let me do this integration on theta 0 to pi by 2, and see this is sin theta d theta, okay, sin theta d theta. So sin theta d theta integration will be minus of cos theta. Let me just get this integration value itself, sin theta d theta, here theta is equal to 0 to pi by 2, okay. So this will be minus cos of theta, and this is 0 to pi by 2. So this will give you value 1, okay. Fine, pi by 2, cos pi by 2 will be 0, lower limit I can take, okay. So due to that, this will be 1. So finally what we are getting as electric field, look, after integrating we are getting the electric field, here I'll write, we are getting 2k lambda divided by r, isn't it? This is what we are getting for the semicircular arc. Now look, let me write down this k. So k is 2 pi, sorry, 1 by 4 pi epsilon naught, and here in this given problem r is a and lambda. So what we are getting? So lambda by 2 pi epsilon naught a, lambda divided by 2 pi epsilon naught a. So this is the electric field at the center due to this semicircular arc. See, from the formula also we got the same answer, right? And this is the way to derive the answer. Okay, so I think I'll just stop it here with this. In the next session we'll continue with this electrostatic and furthermore good problems. Okay, we'll take, and I'll try to make your understanding more clear. Okay, so thank you for your patience. Bye for today.